and Amatya, I guess. So yeah, what do you?
Hey, am I audible? Yeah, okay. Yeah, I'll be discussing our decomposition approach to solve the weighted case server, and yeah, this is joint work with Ashish and Amatya, who are among the audience. Okay, so yeah. Fine. Yeah. Okay, so I'll define the weighted case error problem. In the weighted case error problem, you are given a metric space. A metric space is basically a bunch of points, and and there's a distance defined between every pair of points. And there are k servers on this metric space, and each of these k servers have weights. Like in this diagram, there are 3 servers, and their sizes correspond to their weights. So at each time you get a request at some point in the metric space, and this red point here corresponds to a request, and you serve the request by moving at least one of the k servers to the requested point. So here there are some bunch of requests, and you have to serve this request by moving at least one of the server to the requested point. And yeah, so now the objective of this problem is to minimize the total weighted movement. The weighted movement here, I mean, like, let's say a server with weight wi moves some distance di, you pay wi times di. So here, I mean, the server weight w1 is moving distance d1 and d3, so you pay w1 times d1 plus d3 and so on, correspond. So in the objective is to minimize the total weighted movement. And since this is an online problem, I mean, you have to set the current request before seeing the future set of requests. And just like any other online problem, you analyze any algorithm using the compute ratio, which is the worst case ratio of the expected algorithm's cost to the optimal cost. So that's the definition of the weighted case error problem. And if let's say all the weights are equal, then this is the standard case error problem, and this has been studied for multiple decades. And the best known upper bound is like Otsavian and Papadimitrov from 90s, which is 2.1 competitive on any metric space. And the best known lower bound was recently given to Bubek et al., which is log square k. Now, using this unweighted k server problem, you can get a trivial bound for the weighted k server, which is wk or w1 times the competitor ratio of the unweighted k server. This is not, I mean, this is not desirable because the ratio of the weights could be arbitrarily large, and I mean, this could this competitor ratio could be some arbitrarily large value. So the challenge is to get a computer ratio that just depends on k, which is the number of servers, and that is independent of the metric space and the weights of the servers. It turns out that weighted k server is a very hard problem, and even for 2 servers, I mean, it's a very hard problem. So for 3 servers, I mean, it's an open problem to get C complete algorithm for any C on any metric space. And yeah, this is still an open problem. So now, I mean, we try to focus on simple metric space. So how hard is weighted k server on simple metrics? So what do I mean by simple metrics? We consider one of the simplest metric space, which is the uniform metric space. So a uniform metric space is a metric space where distance between any 2 points is 1. And this weighted k server on uniform metrics has been studied by Fiat and Rickling in 90s, and they gave a W exponential upper bound. And this upper bound was matched by Bansal, Elias, and Commerces in 2018, where they gave a W exponential lower bound as well. So, I mean, it is known that the deterministic computer ratio of weighted k server uniform metrics is W exponential. Now, now in the randomized models, chip level distribution, they W exponential upper bound memoryless algorithm, and they also showed that this W exponential bond is tight on any memoryless algorithm. So the only thing left is randomized bonds with memory, and myself and Chiplanka gave an exponential lower bound, any randomized algorithm with memory. So as you can see, there is clearly a large gap between the best known upper bound and the best known lower bound. Yep. Memoryless means, I mean, you don't, I mean, you don't, I mean, it doesn't depend on what the past requests are. Given a request, you just solve the request by some probability distribution. You don't take into account of what happened in the previous set of requests. Any other doubts? Okay, yeah. There is still a large gap between the best known upper bound and the lower bound, and yeah, Gautam, yeah.
Like an oblivious sort of address.
Yeah, an oblivious, yeah.
So if I am memory,
Yeah.
that's basically
Yeah.
you're sort of restricting the algorithm's power.
Yeah, so memoryless algorithms, I mean, the oblivious, I mean, the adversary is oblivious, or I mean, online adaptive, both are sort of same, yeah.
Okay, but for memoryless, it's the same
Same thing, but
okay. Yeah, okay.
but with the memory, it's oblivious, like that's the exponential lower bound.
Yeah, so the point where I was trying to say is that without memory, you're fighting away sort of the unknown algorithm has a steep ask.
Yeah.
And it's basically the adversary, it's almost like an adaptive adversary.
Yeah, it is. Yeah, both are equivalent, like, I mean, online adaptive or oblivious, or memoryless. Okay, so now the open question is, like, can we get a randomized algorithm that is exponentially competitive in K? So that is what our, I mean, aim is. And so before going into our approach, I will define like few notations that are useful in explaining our approach. So any solution to the weighted case error problem can be decomposed into two parts. One is a service pattern and the other is a labeling. So what is a service pattern? So first, let's consider the moments of this server W1. It partitions the entire timeline into sets of intervals, where, I mean, each interval is where that server is at one position, and the next interval it moves to a different position. And so here each vertical line here sort of represents when the server is moving. And now if you consider the moments of all the K servers here, there are 5 servers. So each of these will partition the entire timeline, and this entire thing put together is what is a service pattern, where each level corresponds to movements of some server. And since we are dealing with uniform metrics, the cost of the service pattern is the cost of this service pattern is essentially Wi times the number of intervals there are, because, I mean, distance within any 2 points is 1. This is still not a solution to the problem, because, I mean, you have to specify when each server is moving. So that's what the labeling does. So in the labeling, you label each interval with some point, and I mean, so here, I mean, you can see that, I mean, at each of interval, I mean, the server will be moving to a different point that is labeled that point. And now, to satisfy the feasibility, so a feasible labeling must have, I mean, a labeling is feasible if each request is covered by some interval which is labeled by R. So if every request has to be satisfied, then some interval should be covering that request which is labeled by that R. So that's a feasible labeling, and I mean, we say, we call it a service pattern that is feasible as a feasible service pattern that has a feasible labeling. That's it. So, yeah.
First request red.
I think it's not red, it's pink. W3, yeah. Yeah.
Not sure if they understand. not sure if I understand the picture correctly, but
Okay.
so what do these boxes represent at the W1, W2, let's say,
So those intervals represent, I mean, where I mean the server is at the points during the interval, and then the next interval it is moving to a different point.
like I don't see why. So W1 is a server, right?
Yeah.
So is why would two servers both swap positions at a certain time step? That should not happen, right?
Okay. I mean that swapping is, I mean, yeah, you may not swap, but okay, they can move at the same time. But yeah, I mean,
I understand. Yeah.
just an example. Let's say, yeah, you can move multiple servers, and I mean, yeah. Okay. So now, I mean, I'll quickly, I will briefly explain what our decomposition approach is. So first, we decompose the weighted case server into two relaxed versions. The first relaxed version is called service pattern construction. I will shortly define what this means. And the second relaxation is called weighted case server with reveal service pattern. And the idea is to sort of compose them and maybe solve these two separately and compose them to get a better algorithm. So yeah, the first relaxation, which is the service pattern construction. In this problem, the input is request sequence request sequence in online, and so yeah, the points represents the request sequence, and the output is an unlabeled feasible service pattern. So your output, you're not satisfying the request, you're just outputting a service pattern that has to be feasible. So there are a couple of things to notice here. So first thing is that, let's say you get a new request, you can only extend the service pattern. You can't change the movements that you have done in the past. So for any new request that you get, you can only extend the service pattern to output a feasible service pattern. You can't output something entirely new. And it should be a feasible service pattern. By that, what I mean is there should be some feasible labeling. As long as there is some feasible labeling, you are good. And this feasible labeling, as you get into the request, could be entirely different. It need not, this labeling need not extend. It could be, the feasible labeling for the new output could be entirely different. As long as there is some feasible labeling, your output is good. So, yeah, those are the two important things to notice in this output. And now the goal is, again, yeah, same. You compete with the optimal offline cost. Yeah.
We only extend, you don't have to. Why is that? Like, if we don't extend, like, we not
what do you mean by we don't extend?
In a sense, like if we put a new boundary. So, okay, so what do you mean by like if we get a new request, we should only extend?
Yeah, you can't change the movements. Like, okay, so given this new request, you can't change these movements that you have done here. So, you can only either extend this or draw some line here or move
Draw
some
some line
line.
and extend, that's possible.
You can only draw some line here or don't move anything if it is fine. Yeah, whatever
Okay,
makes it feasible, and yeah.
okay, fine. So by new request, you mean just another request?
Yeah, just another
One
request.
of
Yeah,
the previous.
yeah, just another request. Yeah.
Serve every request.
You're not serving any request here, you're just outputting some feasible service pattern.
Served every, like, we
Uh,
should have placed a server
Uh,
at wherever.
You are not moving, you are just outputting when you are moving the service, not where. So as long as there is some labeling, you are good for this. So this is a relaxation, you are not serving all the requests. So it's like a relaxation of. Okay. So yeah, the goal is to compete with the optimal offline, and yeah, the output could look something like this when the request sequence ends. And one trivial fact to observe here is that if you have any alpha competitive algorithm for the weighted case server problem, it is also an alpha complete algorithm for this relaxation. I mean, that's a simple exercise if you want to work it out. And yeah, now I'll move on to our second relaxation, which is weighted case server with trivial service pattern. Yeah, in this problem, your input is sequence of request, and along with this input, you are given an available feasible service pattern, which is this one. And now your goal is to serve all the requests, which is basically outputting a service pattern with a feasible labeling. Now, one important thing to note here is that your output service pattern need not be same as the input service pattern P. So it could be something entirely different. So yeah, it could move servers which when the input service pattern is not moving, or it could move some additional servers. But I mean, as long as you are serving a request, you are good. And here you are competing with this input service pattern P and not with the optimal offline algorithm. So now, I mean, a trivial fact, like if you have an alpha complete algorithm for the weighted case server, it is again an alpha complete algorithm for this relaxation. So, yeah, any questions on this definition?
So, how are you ensuring that in the previous step, the previous, this step?
How do you ensure that it's always feasible? One thing you can do is you can always move one server, like some server, and that would always remain feasible.
Okay.
So if you just want to output a feasible service pattern, you can move servers, and I mean, one server W1, and that would ensure feasibility. So yeah. Now on to our first result, which is this composition theorem. Suppose there exists an alpha 1 COMP2 algorithm for this service pattern construction and an alpha 2 COMP2 algorithm for this for the weighted case server with the reveal service pattern. Now let's see what we can do with this. So yeah, the input is a request sequence in an online way, and yeah, you feed this input to the algorithm A1, which has the same input, you get request sequence online, and its output is an unlabeled feasible service pattern. Yeah, and I mean, one thing to note here is that this request sequence and this service pattern is done online. I mean, I did not animate that, but yeah, you get the request sequence online and it outputs the service pattern, and now you take this output of A1 and the request sequence and give this as an input of A2, and the A2, I mean, it basically serves all the requests taking this input, and now you can think of this entire thing as an algorithm A, which takes the input as a request sequence, and the output is service pattern with a labeling, which is essentially you serve all the requests by moving the servers. Now and this is an algorithm for the weighted case server problem. And now let's analyze the cost of this. So the cost of the output of A1 is at most alpha times opt, because that's from the guarantee that A1 is alpha 1 complete algorithm. And the cost of the output of A2 is at most alpha 2 times cost 1. Because, I mean, the algorithm for weighted, I mean, the reveal service pattern problem, it competes with the input service pattern. So cost 2 is at most alpha 2 times cost 1, which is essentially alpha 1 times alpha 2 times opt. Now, yeah, we get an algorithm which is alpha 1 times alpha 2 COMP2 for the weighted case server by composing these two problems. So yeah, that's our first result. Like, you can decompose the problem into these two relaxations and compose them back to get alpha 1 times alpha 2 COMP2 algorithm. Now the second result, which I'm going to just state, is that we also give exponential in K-square competitor algorithm for the second relaxation, which is the weighted K-server with the reveal service pattern. So now we also show that the exponential lower bound for the weighted K-server also holds for this relaxation, which is weighted K-server with the reveal service pattern. So, I mean, there is still some, I mean, it is almost understood that this problem, the competitor ratio is exponential in some poly K. But there is an open problem where, I mean, if you design exponential in poly K competitor algorithm for the service pattern construction, this is an open problem, and if you can do it, then yeah, we can obtain an exponential in polynomial in K competitor algorithm for the weighted K server, and that almost matches the exponential in K lower bound. Even the lower bounds for this service pattern construction are also not known. I mean, any non-trivial lower bound or any lower bound is not known either, and that would also be a good direction. I mean, to understand this relaxation, which is the service pattern construction. So, yeah, that's it from me. Thank you.
Yes.
For two servers, what's known?
For two servers on uniform matrix, for deterministic, it's known that it's 5 competitive, and even the lower bound is there. But for randomized, I mean, there's still a gap.
Okay, this is just not specific to this maybe. So I happen to remember there was a work function algorithm which was supposed to be, whose analysis was supposed to reveal the best possible bound for a weighted case of a problem also, right?
So yeah, I mean,
We happen, like, what's this? Do you use that or do you use some other?
for the exponential upper bound, you mean, or?
No, I'm just generally asking, is that the road you travel, like the?
You use completely different ideas.
I mean, there is a deterministic algorithm using work function that is W exponential competitive, but there is nothing known, I mean, for randomized bounds, and yeah, that's already done by Bansal et al. I mean, they did.
Sure. So we had a nice discussion during the talk itself. Thanks, Nikhil. Yeah. One question. So he mentioned deterministic upper bound on uniform metric. Anyone? Deterministic upper bound on uniform metric. Do you? Do you? Okay. Yeah.
लॉगिन आईडी डाल दो इसको भी एक सेकंड रहने दो इसको भी रहने दो इसमें से लॉगिन आईडी डाला इसमें तो डोंट कनेक्ट ऑडियो हाँ कुछ भी सब बंद रखना तो सब बंद रखना हाँ जस्ट शेयर द स्क्रीन कंप्यूटर ऑडियो अच्छा ठीक है कंटिन्यू म्यूट तो है शायद you just go and share yes I'll just check this slide change এখান থেকে করবে নাকি এটা তো কানেক্ট হবে না এখন যাইট করবো এটাতে মোস্ট পসিবল কানেক্ট করতে গেলে এটা বলুন আচ্ছা এটার সঙ্গে কানেক্ট করে যাবে নাকি না এখান থেকে করতে হবে কোনো অসুবিধা ইয়ে তো অটোমেটিক ঠিক আছে टेम्परेरी चेंज कर देगा नंबर ठीक है लेफ्ट 3 से
So this talk is by Wade Gupta on matching and low velocity graphs in dynamic streams. He's from IBM Research.
yes am I audible okay can everyone hear me okay good okay so thanks for being here I'll talk today about matchings in low velocity graphs in dynamic streams. I'll explain what each of those words or terms means as we get to them. I won't assume that everyone knows the requisite background. So let me give you the talk outline at first. So I'll set up the problem. I'll give you all the relevant definitions, some motivation for why we care about this problem at all. Okay, this is fine. Okay. So I'll give you some requisite background, and then I'll briefly mention our results and also like lead up to it with some results that are known. And then I'll give everyone a one warm-up proof. This is going to be the sort of technically most demanding part of the talk, but it will still be a sketch of a proof. It's not going to be our proof. It's going to be someone else's proof that we use very crucially in a lot of our results. And then once we do that, I will just go through a couple of the main results that we have and try to give you a sense of how we use the warm-up proof and similar results to get our bounds. And then I'll end with two open questions that have been bugging us ever since we have done this work. And so I should mention that this is joint work with 3 other co-authors. So this is Christian on the left from Bristol, and then Andrew McGregor, who was my PhD co-advisor at UMass, and then on the right there is Kwong, who is a PhD student at UMass as well. Okay. So let me set up the problem at first. So okay, this part I don't think I need to sell to anyone. So most real world systems that come up consist of a set of some sort of objects or agents with some relationships between them or between pairs of them. So that's most conveniently represented by means of a graph. And so graphs are the objects of interest. And of course, graphs are incredibly versatile, mathematically extremely useful, naturally beautiful objects. But also in real life settings, most graphs that come up are incredibly large. And they're also, the examples of graphs, obviously, the internet and social networks and DNA and blast sequences, what have you. They're quite large to store in memory, right? So this is just a Google search picture of the internet. This is really one portion of the internet that I drew up got from somewhere. This is just a tiny portion of the internet. And of course, this is something that you cannot store in your memory. And therefore, in particular, you cannot use classical algorithms on these very large and constantly evolving graphs, right? Because classical algorithms typically assume that you can store the whole graph in memory and you can pull from whatever part of it that you want. And so we therefore have to use techniques such as sketching or streaming or some kind of sampling process or some kind of like going to zoom into a graph in order to make any progress meaningfully. So that's where we get graph streaming from. I'll talk today primarily about the dynamic streaming model, which is where your input comes to you in the form of a graph presented as follows. You start with a bunch of nodes and no edges at all between them. It's sometimes called an edgeless graph or sometimes called an empty graph as well. And what you get is a sequence of edge insertions and deletions. And that's going to be the stream of the model. And so what you're allowed to use is a small limited amount of memory somehow. You cannot store all the insertions and deletions that came in. You cannot store the entire graph. But somehow you have to make intelligent choices as to what to store and what not to store. And then at the end, you get a final graph. And then you want to determine some sort of properties of that final graph.
So of course, if you had, squared memory or something like that, where n is the number of vertices, then this is no problem, right? You can just recreate the entire graph. You have the whole graph at your disposal at the end of the process. But in general, you don't. You have a very much smaller number, in fact, a sublinear amount of memory in order for these questions to be interesting. There are, of course, classical streaming results outside of graph streaming. So that includes things like heavy hitters. You have seen all of these in your algorithms classes, quantiles, and so on and so forth. In fact, NetSet can also be seen as in a particular streaming version. Graph streaming also has included work on distances, eigenvalues, and so on and so forth. I'm by no means an expert on most of these results, but I'm told that there's a very rich body of literature on this. So as an example, if this is your starting empty graph, you can notice that you can have a sequence of edge insertions like this. So, there's 4 edges get inserted at first, but then you might lose one of these edges, and so on and so forth. And the point is you have a very tiny amount of memory, so you cannot possibly choose to remember all these pairs of edges that get inserted or deleted. And then at some point, this process stabilizes and you get the final graph, and you want to ask questions about this final graph. Make sense? Okay. The particular graph property we're interested in is matchings, very much in line with the rest of this session or these couple of sessions. So matching, of course, is a set of edges that don't share any endpoints. So that's an example of such a set of edges. And you might notice that there's 3 red edges in this. I don't know if the red is visible, but these 3 edges form the matching. And you can easily convince yourself that you cannot do better. You cannot find 4 edges in this graph that are all pairwise independent in this sense. So this is a maximum matching. And the problem of interest is that we would like to estimate the size of the maximum matching in G. That's sometimes going to be that's going to be denoted by mu G. And I just want to make an observation at the outset that this is different, this is distinct from a very related problem which asks you for an explicit maximum matching. So this is a size estimation problem. If you are asked to find a maximum matching, in general, you might need, omega of n space, linear amount of space to just output the matching in the first place. So because that might be the size of your output, so you can't do a lot better than that. So in general, I just want to draw this distinction here. These both have different bodies of literature, but they're quite related as problems. And then the last definition that we'll deal with is that of low albericity graphs. So a graph has albericity alpha if its edges can be partitioned into alpha edge disjoint forests. That's the definition of albericity. It's a very natural notion of sparsity. If any of you have, many of you have already worked with albericity, some of you might have worked with degeneracy, which is a related concept where I think they're related by a factor of 2 or something like that. It's a very natural notion of sparsity. And in fact, bounded albericity is a notion that generalizes planar graphs, bounded degree graphs, and bounded tree width graphs. So it's a larger class of graphs than any of these things. Okay. Sorry. So in previous work in the streaming literature, so now you have a graph that comes to you in the form of a dynamic stream, and we're asked at the end what is the size of the maximum matching in this graph. Most of the previous work that has been done, and the vast majority at least of the previous work that has been done on this problem has involved a single pass over the stream. So in that setting, there's scores of works that I can put up on this slide, but I'll just zero in on a few of them. From the upper bound side, there is, by the way, for the purpose of this talk, think of alpha as more or less a constant. We give results in terms of general alpha, parameterized by alpha. But a lot of these results will make more sense or be more interesting or be more tangible when alpha is a constant. So constant diversity graphs. So there's a constant approximation known in sublinear space into the 4/5 space. This is a result due to Chitnis and others from 2015. This bound, the space bound of n to the 4/5 was improved to n to the 2/3, also a constant approximation by Cornwood et al. In 2017. But this is a conditional upper bound that was given. The condition is that it assumes that the stream length is linear in n, in alpha n rather. So what that means is that if you have this extra guarantee that every edge is inserted or deleted on average a constant number of times, then you can do better. You can improve the space required. At a sort of a different vein, Asadi et al. Have a result that's of this form. You have this n squared over alpha to the 4 approximation. This is only sensible when alpha is quite large, when its alpha is super constant. So if you want a kind of a trade-off result, you have this kind of an upper bound. And then there's this upper bound, which we'll dig into a little bit more in the second half of this talk, where you have, I guarantee that that there's some upper bound, any upper bound on the maximum matching, let's call that upper bound K, then you can, in quadratic space in that K, give me an estimate of what the matching size is. And we'll go into this result because we'll use this critically in some of our results. And this is a result due to Chitnis et al. Again, and then another of Asadi's papers, you can just derive this result from that. Okay, so that's the upper bound side. I can mention many other things. Fandieri has some work done, which is actually exactly our problem, but on planar graphs. We generalize that result. So there's many more works that can go up here, but these are the ones maybe to keep track of. From the lower bound side, this is a very important result, which we'll contextualize in a second. But Asadi in a different paper, in a 2017 paper, showed that any constant approximation, any alpha approximation, would require this kind of space. So in particular, any constant approximation to this problem would require root n space in a single pass. So these are all one pass results. Okay? And that's sort of a magic number to keep in mind for the rest of this talk. Root n is somehow a barrier. And in fact, they went on to show that if you want to approximate it even more, if you want to approximate it to within 1 plus epsilon, then you need space which is nearly quadratic. You need almost the entirety of the space that you're given into the 2 minus some epsilon. Okay, so this is the sort of landscape. We'll mention our results in one slide, and we'll go a little bit more into depth in that. So we're dealing with alpha arboricity graphs G. We have the following results. Okay, so let me try to go through these slowly one by one. So if we start with a p-pass algorithm, so p is any parameter, which gives you a 1 plus epsilon approximation factor. We deal with multi-pass algorithms, so we're allowed to go through the stream multiple times. So if you allow yourself p passes, then you have this horrendous looking number over here. That's the space used. The details of the number are not important, except to show that there is this sort of exponential decay in the number of passes and the size of the space used in your algorithm. So, if you allow yourself more passes, of course you need less space. And as a corollary to really wrap your head around that theorem one, if you plug in log n into for p, you basically get a space k algorithm for approximating the matching. I should say that k, anytime you see k is just any upper bound and the size of the match. You are supposed to know k beforehand for whatever reason. If someone gives you an oracle gives you an upper bound, then you have this result. Okay, so that's the first kind of trade-off kind of a result that we have. A second result is a 2-pass algorithm that gives you a constant approximation, and alpha plus 2, we remember alpha as a constant for the purpose of this talk. So it gives you a constant approximation to the largest matching size in space into the 3/5. This improves the current norm into the 2/3 conditional lower bound as well, conditional upper bound as well. So we bring that down. And in fact, combining elements of all of these proofs, this is sort of our main theorem, is that in 3 passes, we get a constant approximation in size root n, which is the theoretical lower bound in a single pass. So what we essentially show is that at the cost of 2 extra passes, you reach that lower bound as well, you match the lower bound in the upper bound. And yeah, so there's a very valid kind of thing to ask. Oh, okay, so 2 passes, extra passes, of course, gives you more power. So what is this really buying us? And I would say that one thing I should note here is that for all we know, increasing the number of passes to 200 or 1,000 or anything like that does not seem to bring this root n barrier. There's no known algorithm that gives you a little o of root n space algorithm with a much larger number of passes as well. Okay, so that's the summary of the results. Yes, question.
Number of passes and that problem.
Yes, so the question was in theorem one, isn't there a trade-off between the approximation factor and the number of passes? Yeah, no, this is, you assume that you want an epsilon approximation factor. The only trade-off is over here. This does require you to be magically somehow, or like by an oracle given an upper bound on K. But apart from that, this is as you see. There's no hidden constants or anything like that here.
So, but is it a meaningful question to ask instead of space, the
Yes.
improvement should be number of passes yields better approximation?
That's a great question to ask. So
Have a p-task type thing. So.
yeah, okay. So that's a great question to ask. So instead, exactly, you can optimize either of these two columns absolutely with respect to the number of passes. We haven't looked into how to optimize the approximation factor by somehow, giving ourselves this amount of space or something like that. But that's a great question to ask. Absolutely. Thank you. All right. Okay. So I'll keep going. We'll go through a warm-up proof. Someone once told me that a good talk should have one joke and one proof, and they should not be the same thing. So I'm going to try this is the proof part of it. I guess that was the joke part of it. Okay, so dynamic strings, estimating matching size. So let me repeat a result that I had mentioned on an earlier slide, which is the following. So if you somehow have this guarantee of an upper bound of K on your maximum matching size, then that size, you can find that size exactly in about K squared space. So this is Chitnis et al. There's some related results to Ribery et al. So we're going to go into the details of this proof. How do you prove something like that? The takeaway, remember, is the upper bound, space quadratic on that upper bound, you can find the matching exactly. It's not just the size, in fact, because you have K squared space, so you can just output the matching explicitly. So main idea is, of course, to sampling somehow. What kind of sampling, right? So one thing that I should mention, if you haven't seen streaming literature before, is that it is definitely possible to uniformly sample in your streaming model. So in insertion-only streams, that's quite easy to see. Insertion-only is when no edge is ever deleted, you only have insertions. In an insert delete stream or a dynamic stream, it's a little harder to see, but it's possible. Let's just take it as a black box. You can use sort of sketching techniques to uniformly sample edges. But uniform sampling is not great for estimating maximum matching sizes. Does anyone see why? Like, what is a graph for which uniform sampling doesn't really reveal, as it were, the maximum matching? Thoughts? Okay, so I can tell you, like, it's pretty kind of a gotcha question. So imagine that you have a clique which is just sublinear in size. So you have a clique of size, n to the 0.99 or something like that, and then the remaining linearly many vertices form a perfect matching. Now the thing is, the best matching in this graph is determined by this tiny fraction of your edges. But if you uniformly sample edges, most edges that you ever draw will be part of the clique. So you will never get to see sort of these extra edges. And that's somehow important. So you can't just sample blindly. So what do? The technique here that's going to use is called, it's a very evocative name. It's called sample nodes and pick edge. So the spoiler is in the name for how you sample these things. It's also, the other thing I like about the name is that it is a very convenient acronym because it's SNAPE, so we can call it Snape sampling if you like. Okay, so it is Snape sampling. What's the idea of Snape sampling? Here's how you get a single Snape sample. You have your graph. Remember, the assumption here is that you have some upper bound K that's given to you on the matching size. The way you get a sample is first you sample each node with probability 1/K, and you delete the rest of the graph. So let's say you have sampled all the nodes and you have these red vertices remaining. You get rid of the rest of the graph. And then out of all the edges that remain, you pick a random edge. So let's say you pick this edge. This is also random. So this two-step process gives you a single edge, and that's the result of a single Snape sample. Okay? So what's the idea? Why are these things useful? It turns out that here's a theorem that's going to be the critical theorem for this proof, is that if your guarantee holds, if K is an upper bound to the maximum matching size, then about K squared Snape samples are guaranteed to contain a maximum matching in G. If you take enough samples, then you will preserve one of your maximum matchings. Okay? So how do we prove something like that? So the overview is fairly simple. So let's say that a node in the original graph G is heavy if it has high degree, if its degree is at least 10K. Remember what K is an upper bound on the matching size. and an edge, let's call an edge shallow if neither of its endpoints is heavy. Okay. So here's a shallow edge. Its endpoints are sort of 90 degree, low degree nodes. And here's a heavy node. It's just a high degree, very high degree vertex. This is going to be a lemma without proof that we're going to use. So suppose you get a subgraph G prime of G that satisfies the following conditions. That subgraph is guaranteed to contain a maximum matching of G. The conditions are the following. That subgraph has to include all the shallow edges of G, and every heavy node in G has to be pretty heavy in G prime as well. Okay? So if you have these two conditions in your subgraph, then that subgraph, you have reduced the problem to just that subgraph, is what I'm trying to say. And you can notice in the previous example of a clique plus a perfect matching, this is fine because the problem there were all these shallow edges. That was the isolated perfect matching. So if you have this guarantee, this first point, there's been a lot of heavy lifting here. If you have this guarantee, then at least that graph is no longer a problem. Okay, this I'll leave as an exercise. It's actually quite straightforward to see. It's just pure graph theory argument. But let's prove this lemma in the context of Snape sampling. So what do we want to show? We want to show that if you have k-squared Snape samples, your resulting subgraph, your resulting set of edges, satisfies this property. Okay. So I will go through the first. There's two cases: shallow edges and heavy nodes. So I'll go through the first one in slightly more detail. So let's fix a vertex cover W of size at most k. Why does this exist? Because this is like a brownie question. Yeah, I can hear some murmurs. Exactly. So you have this upper bound on the size of the maximum matching. And you know the maximum matching is the same thing as has the same size as the minimum vertex cover. So you have some vertex cover of size at most k. Okay, so let's assume that that's a shallow edge in the original graph. Under what circumstances would that be preserved under Snape samples, right? So one way in which that edge UV is preserved is if U and V are both sampled during the vertex sampling part of it, but no other nodes in the vertex cover or in the neighborhoods gamma U and gamma V of U and V are sampled, right? So if that happens, then notice that the only remaining edge is the edge UV. All other edges disappear because they're either adjacent to U and V, but those disappeared, or they're adjacent to something else in the vertex cover, and that disappeared. By definition of the vertex cover, right? And so what's the probability of that? Well, you can see that the probability of that is about this because you want U and V to remain, so that's the P squared. You want everything else in the neighborhoods of the vertex cover to go, so that's 1 minus P to something. And notice that these things are linear in K by definition because UV was a shallow edge. That means the neighborhoods are at most K in size, and the vertex cover is at most K in size. And so this whole quantity, this probability is at least 1 over K squared, right? Like P is 1 over K. So the 1 over K squared comes from the P squared. And notice that this is just 1 minus 1 over K to the sum function of K. So it's somewhere between 1 over E to some 1 over E to the 50 and 1 or something like that. That part is a constant. So that means by coupon collector essentially that after you have taken enough repetitions, after you've taken K squared log K repetitions, that edge, you're guaranteed to have picked that edge. Part of the proof. That just means that you have had enough Snape samples to be guaranteed to pick this shallow edge. Right, I'm going to rush through the second part quite quickly. So the heavy nodes case is quite similar. You again have this vertex cover, you have this heavy node. One way to preserve that heavy node as quite heavy in the resulting graph is if everything else in the vertex cover disappears. If that happens, you're left with a heavy node with a whole lot of leaves around it. Right? A heavy node's definition was it has degree at least 10K. If everything else disappears, it still has degree at least 9K because at most, the vertex cover has disappeared through that. So the probability of that happening is roughly this. That quantity works out to about 1 over Q. So with 1 over Q, probability a heavy node is preserved. And so if you have enough repetitions, the idea is that you have at least 5K edges you sample that next to this heavy node. So this heavy node will be quite heavy-ish in the subgraph as well. Okay, so the upshot of all of this is you have given yourself this many repetitions, K squared log K repetitions of the Snape sampling, and you have preserved the two conditions of the lemma I showed you earlier, which means that the sparsified subgraph G prime is now going to be a good estimator for the largest matching size of the large graph G. Make sense? So that's the sort of technical detail of the talk over. Okay, there's some details here that I brushed under the carpet, so talk to me afterwards if you're interested. Yeah.
Right.
Okay, the question was, did I assume the graph to be bipartite? No, I have not assumed anything here except for. So the original graph, if you're talking about, I have made no assumptions on the original graph except some upper bound on the size of the largest matching. But this event, if this happens of one particular node being sampled and everything else in the vertex curve being removed, then you're essentially left with a star plus a bunch of isolated nodes. So that is bipartite sort of by construction, by design. Okay, right. So without the first okay, so I should replace it by 8K or something like that. Yes, okay, great. That's a good question. So the vertex cover has size at most 2K. There's a large inner vertex cover. That's a good point. Yes. Okay, so let me just take you through our main results. Just two of them. So before we get to that, I'll just describe one magic lemma. This is also not from us. Here's the magic lemma. Here's a graph. I have weighted the edges by something, by some numbers. So this will appear magically. Also, this is a density graph, roughly. The magic lemma just says, if each edge of a graph has this weight that's given roughly this quantity, it's the minimum of this inverse degrees of its two endpoints, then the total weight, so the sum of all the edges, sum of the weights of all the edges of this graph, that is a good alpha plus 2 approximation of the maximum matching size. So this is a lemma due to Andrew McGregor and his student Sophia from SOSA 18. And it just says that if you have a way to estimate these weights, you will also have a way to approximate the maximum matching size up to with a possibility of alpha-ish as a factor. Okay. So remember the magic lemma if you can, and then remember the slides from before, the part from before about the K-squared space algorithm. So it's just those two tools that give you a sense of how to implement our two-pass algorithms. But again, our two-pass algorithm just says this, that there's a two-pass algorithm through the stream that achieves a constant approximation of the maximum matching size using space into the 3/5. So let me prove something a little weaker. Let me replace that into the 3/5 with an into the 2/3. This is also a new result. This actually matches Qualmod's upper bound as well, but Qualmod's upper bound had a condition on the total length of the stream. This one does not. But it's a similar technique of 2/3. So how do you prove this? The matching is small. Either the matching has size at most, cube root of n. And if that's the case, you can use snake sampling to estimate that matching, in fact, to output that matching in space into the 2/3. Right? Because that's quadratic in the upper bound of the space. Otherwise, what you do is in the first pass, you sample into the 2/3 edges uniformly from the whole graph. And then in the second pass, you can store these edges explicitly because you have enough space to store into the 2/3 edges. And so in the second pass, what you do is you estimate the weights by the magic lemma of these edges that you have stored. Notice that the magic lemma is more and more useful if you have more and more edges. And somehow you use that to estimate the total weight, which you already know is an alpha approximation, alpha plus 2 approximation to the maximum matching size. And we've assumed here that alpha is a constant for at least this part of this simplified version of the proof. And that's it. That's the two-pass algorithm. Okay. So very briefly, the sketch of the three-pass algorithm. So the three-pass algorithm is a sort of a main result that says that there's a three-pass algorithm that achieves a constant approximation using space about root n, which is the theoretical lower bound in one pass. So here's what happens in all of the passes. I just tell you what it does, but if you want the details, come find me afterwards. So in the first pass, we sample about root n edges and use those edges to identify the set of heavy nodes. So to identify the set of nodes with high degree, where high degree the threshold is different as root n. In the second pass, we sample root and edges that are not adjacent to anything among the heavy nodes. So those are sort of your shallow edges, if you like. There's another root n of those things. And in the third pass, that's similar to this, the pass algorithm, you learn the weights of the sampled shallow edges and use those to compute the weights of the part of the graph which is not heavy. So just the part of the graph which is G minus the set of heavy nodes, and you estimate the maximum matching size in that, and you can just return the size of the, oops. Oh, you cannot see. Okay, I can't see. Okay, something disappeared from my screen. Trying to figure that out. Okay, I think I just have 2 more slides, so maybe I can just the internet just gave way. It's okay. Okay, my Zoom is restarting, so it always happens in some talk or another. Okay, in the interest of not keeping, I will just maybe just describe. I remember the rest of the slide. That was the last slide I really open question. So all you do in the 3-pass algorithm essentially is you remember the size of the set of the heavy nodes, and you estimate the size of the maximum matching of the remaining graph, and you just output the size of H plus the size of the maximum matching in the rest of the graph. And that by the previous lemma that we showed is a good estimator for the total matching size. Okay, so if technical issues haven't happened, I would have shown you my open question slide. It just has really 2 questions, and I'll only say maybe one of them because we're running out of time, and I know you all want to break for lunch. So the real question that we want to make progress on is the following: can we beat the root n barrier? So the root n barrier seems to be a very inherent problem in this setting, and we think that this would be an easy question to answer when we started working on this problem. We know that that's a lower bound for 1-pass setting, so that has neither been improved, that has neither been pushed past root n to like maybe into the 0.501 even. It has not been beaten even with even allowing yourself many passes. So the big open question that we have, which we think should be easy to make progress on, is for a constant diversity graphs, is it possible, is it conceivable to have a 200-pass algorithm that is below, that uses space less than root n or not, strictly less than root n. So okay, so sorry about the difficulties, but that's all I have. So thank you. Questions? So good question. So if you don't assume constant diversity, many of our results are still state of the art for multi-pass algorithms up to a certain amount of alpha. So there is a threshold for alpha after which Asabi's result takes over, and that's definitely the one where you divide by alpha rather than you multiply by some alpha. So those are just objectively better in that case. I don't know what that thing is. It's some polynomial in n. I mean, obviously we can go up to n-ish. So I don't know exactly where that happens, but yeah. So for small alpha, for up to a quite reasonable range of alpha, these are still the state of the art. For 1-pass algorithms, that's the slide that I showed earlier with the current known upper bounds. Those are also the state of the art for that for 1-pass algorithms. We only deal with 1-pass algorithms at all in our work. Good question.
Also, are better bounds known for bipartite graphs? Is the lower bound written for
questions? Are better bounds known for bipartite graphs? I don't know off the top of my head. That's a great question. I would have to check. Yeah, I don't know. So yeah, it's a nice question. I don't really know how streaming literature is affected by sort of the inherent assumption that the graph coming in is bipartite or not. That's a good question.
Also, you have this information of K before the stream.
Good question. So we do assume that you have n and alpha that are known beforehand. You can get rid of I think alpha from or n from one of them if you just know n and alpha or something like that. Like you can estimate the rest. But yes, you do need to know those beforehand. Good question.
Thanks.
Have we tried the known lower bound? Okay, so I think the question whether the known lower bound, whether it's on the space used, it's on the space used. So the only known lower bound is for one pass on the space, and that lower bound is like root n over alpha to the 2.5 or something like that. So yeah, that's what's known.
In terms of number of passes and space.
Yeah, that's a good question. So that's in terms of number of passes and space, that relates to another question from earlier. I don't know. I don't personally know. There might be work about this already, but I don't know about any work that has been done trying to optimize or calculate trade-off results between those two objects, right, while keeping the approximation ratio constant or something like that. I don't know. That's a good question.
Thank you.
Yeah. Okay. Thank you. Okay. Enjoy lunch.
So when the velocity is bounded by alpha, what is the approximation factor for 3 passes? Not. Okay, I get nobody focused. Yeah. Okay, this is the answer. Sorry? Okay.
Make your brownie claim. All right, thanks.
Okay, sorry, we're breaking for lunch. Apart from chess, which will also be available today, there is also magic over lunch. So watch out for people who offer to show you some card tricks. So thanks.